In this video, we're going to look at inverses and radical functions. We're going to find the inverse of a polynomial function. We're going to solve radical equations, and we're going to restrict the domain to find the inverses of certain polynomial functions. So if I were asked to find the domain of question 1a, this is a polynomial function in which it's a quadratic, and the domain is going to be everything because it's a quadratic. I don't have any restrictions in the domain. So my domain in interval notation is -infinity to infinity. Set builder x such that x belongs to the real numbers. On part B, since we know this is underneath the radical, I set what's underneath the radical greater than or equal to. And I'm going to have it equal to simply because it's not in a denominator. I mean, the radical is not in the denominator. So I have 3 minus x is greater than or equal to 0. So I have 3 is greater than or equal to x. Interval notation is from -infinity to 3, which is inclusive, because x has to be less than 3. Interval notation, or set builder notation, is x such that x is less than or equal to 3. The next one, what is the difference between x is equal to the square root of 9 and x squared is equal to 9? Well, when x is equal to the square root of 9, the answer here is just x is equal to 3. However, with this one, when I take the square root of both sides, I'm always told that I have to do x is equal to the plus and minus the square root of 9, so x has to be plus and minus 3. The difference is that -3 squared produces 9, and 3 squared produces 9, so I'm going to get two solutions. However, when it's already set up where x is equal to the square root of 9, the answer is only 3, because x is equal to the square root of a single number, whereas this one I have x squared is equal to 9. I take the square root of both sides. -3 could produce 9, and 3 could produce 9 when I square them. When we are finding the inverses of polynomial functions, the polynomial function has to be 1-to-1, which means for each x there's only one y, for each y there's only one x. When this happens, when I have a polynomial function that may not be 1-to-1, I need to restrict the domain and then find the inverse. So this is our parent function or toolkit of functions, and we know what the graph looks like. The graph looks like here is going to look just like this, where we're going to go through 0, 0, here's y, here's x. And so we can restrict the domain for two ways. We can either do it as x is less than or equal to 0, put it in the curly brackets, which I could write as -infinity to 0 inclusive. Or the second way is I can say x such that x is greater than or equal to 0, which for a set builder is 0 to infinity. Either one of those would be fine to write for the restricted domain to force it to be 1-to-1. Part B here, this is, we know here is y and here is x. We know from the transformations of graphs this has been moved over to 4. So it's going to look something like this. And so we're going to restrict the domain. We can either do one, again, we can take the left side, so x such that x is less than or equal to 4. Notice we are restricting the domain at the vertex. And so then I could write this as from -infinity to +4, because that is the x part of the vertex. Or I could take the right side of the vertex and onward. So I could say that x such that x is greater than or equal to 4. So I could start at 4 and then go to infinity. Since we are cutting it at the vertex, what we're going to do then is we're going to figure out what the vertex is. So the way, remember, to find the vertex, this is going to be the x part of the vertex is what I care about. The x part of the vertex, we also call this h, is equal to -b over 2a. In this case, my -4 over 2, which gives me -2. So that is where my x part of my vertex is, and that's the part in which I cut that. So again, I can choose the left side, which is x such that x is less than or equal to -2. Set builder, and then interval would be from -infinity to -2 with a bracket. Or I can take the right side of from the vertex on, which is x such that x is greater than or equal to -2, and my interval would be from -2 to infinity. If we look at D, the thing with D is that this is the cubic function, one of our toolkit of functions that has been moved up to +3, and it is already 1-to-1. So this is y and this is x. So I don't have to restrict the domain because it's already 1-to-1. For every y, there's only one x. For every x, there's only one y. So this domain, as it stands now, is from -infinity to infinity. And then you're thinking, well, what happens when I have some curves in there, some max and mins on my cubic? Well, then it's not so plain to make it 1-to-1, because you couldn't actually cut it to get all possible x values and all possible y values unless you did it in multiple pieces on the cut domain. So let's talk about the finding of domains of radical functions. Now we know that if our index, which is that small number outside of the radical symbol, is even, anything underneath the radical symbol has to be greater than or equal to 0. But when n is odd, we can have any number we want because we can take the cube root of a negative number all day long. Also, when you include the rational functions, where I have a function f, or a polynomial f over a polynomial g, we know the denominator polynomial cannot equal 0. So when we're asked to find the domains of this function and this function and that function, we look at our index. And those are all square roots. This one's a cube root. So we know with cube roots, based on what we know up here and what we know about cube roots, the domain of this one's going to be straightforward. This is just going to be from -infinity to infinity. There's no restrictions on the domain. But A and B and E have restricted domains. So I have 3 minus 4x has to be greater than or equal to 0. So 3 has to be greater than or equal to 4x. So 3 over 4 has to be greater than or equal to x. So my restricted domain is from -infinity to 3/4 inclusive, or I can write it as x such that x is less than or equal to 3/4. On part B, the only thing I care about is the value that's underneath the square root. I don't care about the +5 because +5 will not bring any restrictions in, because adding a real number is going to produce a real number. So I just have 6x minus 8 has to be greater than or equal to 0. 6x has to be greater than or equal to 8. X has to be greater than or equal to 4 over 6, or 8 over 6. I'm already starting to reduce. So x has to be greater than or equal to 4 over 3. So I'm going to write this as 4/3, comma, infinity. Or in set builder, it would be x such that 4/3 is less than or equal to x. All right, we already talked about C. And with part D, we just set the denominator not equal to 0. So we say 2 minus 5x cannot equal 0. So 2 cannot equal 5x. So 2 over 5 cannot equal x. So interval notation would be from -infinity to 2/5, parenthesis, union 2/5 to infinity. Set builder notation, which is my preferred, which is x such that x does not equal 2/5. That's much easier to write, and I don't have to worry about putting it in order. If we look at E and F, now with E, this is a quadratic underneath the square root. So what that ends up becoming is a polynomial inequality, just like we did in previous sections. So we're going to have x squared minus 4x minus 5 has to be greater than or equal to 0. So I'm going to factor this into x minus 5. X plus 1 has to be greater than or equal to 0. And I can either graph this or I can do a sign chart. I'm just going to do a sign chart. X minus 5 and x plus 1. And this produces x is equal to 5. This produces x is equal to -1. So I'm going to start with x is equal to -1. This is going to give me x is equal to 5. I'm going to put my intervals in here. So this is -infinity to -1, non-inclusive, -1 to 5, and then from 5 to infinity. I'm going to choose a number in each region. So I'm going to say x is equal to -6 because I can. This is negative, negative, positive, so we are above. And since we are positive, our first part of our domain is going to go from negative infinity to -1. Now, this -1 is not in a denominator, and we have inclusive, so I'm going to have a squared bracket there. I'm going to choose something in this region. I'm going to choose 0. This is negative, this is positive, this is negative, so we are below. So it will not be part of my solution because I need, again, the greater than or equal to 0. And then I'm going to choose something over here. Let's choose +6. Positive, 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 I am above. So union that above, which is from 5 to infinity. Let's take a look at f. F is basically a rational inequality. So I have to have x plus 1, x minus 1, all over x has to be greater than or equal to 0. So again, I'm going to do a sign chart. So I'm going to have x plus 1, x minus 1, and x. This produces 0, this produces 1, this produces, or -1, this produces 1. So I'm going to have x is equal to -1, x is equal to 0, and this would produce a vertical asymptote if this was a rational function. So I know that even though I have equality, that anything that will involve a x is equal to 0 will have a parenthesis. And then, of course, my last interval, or my last number, is x is equal to 1. My intervals are negative infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. I'm going to choose something on this region, so I'm going to choose x is equal to -2, negative, negative, negative. So this region is negative, so we are below. So it won't be part of the solution. I'm going to choose x is equal to -1/2. This is positive, this is negative, this is negative, this is positive. So we are above. Now remember, we have equality here, but we don't get to include the 0, so I'm going to have a bracket on the -1, and on the 0, I'm going to have a parenthesis. I'm going to choose something in this region, so I'm going to choose 1/2, and this will be positive, this will be negative, this is positive, this is negative, this is below. I'm going to choose something in this region, let's choose 2. Positive, 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 this region's positive, so I'm above. So I union between inclusive, which is a bracket on 1, to infinity. So that's how you find the domains when you have a rational expression underneath a radical and when you have a polynomial underneath a radical. If I were asked to solve a radical equation, what I need to do is get rid of the square root. So to undo the square root, I'm going to need to square both sides. So I'm going to square this side, I'm going to square this side. On the left-hand side, if I have the square root of 3x minus 3 squared, then what ends up happening, since this is 3x minus 3 raised to the 1/2, raised to the 2, we can see the power to power rule. If I have a to the m multiplied by a multiplied by n, this is a to the m multiplied by n. So in this case, these two multiply, give me a 1. So I'm going to have 3x minus 3 is equal to x plus 4, the quantity squared. So I have 3x minus 3 is equal to x squared plus 8x plus 16. Bring everything to the right-hand side. So I have 0 is equal to x squared, and that's because I have a quadratic. Plus 5x, and then plus 19. Yep, so I subtract 3x from both sides, so I get 5x. I add 3 to both sides. And now what I'm going to do is I'm going to throw this into a quadratic formula. And so in the quadratic formula, I'm going to have negative b, so -5. So x is equal to -5 plus or minus the square root of b squared. So 5 squared minus 4 multiplied by 19 multiplied by 1 all over 2. Now this is the discriminant, and in this case I have 25 minus 4 multiplied by 19. This is less than 0. So that tells me that my numbers will be complex. And since my numbers are complex, my x has no solution over the real numbers. Algebraically, I can find a solution. It'll be complex. But realistically, because of the fact that I'm looking for a number that will produce this, if I have a complex number in here, I'm going to have 3 multiplied by a complex number. I'm going to end up with a complex number underneath the square root. Now over here, it may still work out, but if I'm looking for answers over the reals, then I end up with no solution on this one. So the principle of powers, it says for any positive integer n, if a equals b is true, then a to the n is equal to b to the n has to also be true. You may end up with solutions that are extraneous. So in other words, might come up with algebraic equations with a solution, but that doesn't actually check. So to solve these kind of questions, which are radical equations, the first thing you want to do is isolate the radical. The second thing you're going to do is multiply both sides by what power eliminates the radical. So raise each side of the equation to the power such that you want a to the 1 over n to the n is equal to b to the n, so that this radical will become 1. So that you could solve. You may have to repeat this multiple steps. To get rid of the radical if you end up with more than one radical to do. So you may need to repeat steps 1 and 2. Until you can solve, and then you check solutions. Okay. So as we take a look, the first thing I'm going to do, since I know this is a 2, I need to raise this to a power of 2. I need to raise this to a power of 2. I end up with 3x minus 4 is equal to 1. 3x is equal to 5. X is equal to 5/3. Now I need to check. So the square root of 3 multiplied by 5 over 3 minus 4, does that equal 1? So I have 5 minus 4 underneath the radical does indeed equal 1. This has a power of 4, so I'm going to raise this power of 4 and this side to a power of 4. So I'm going to be left with x squared minus 1 is equal to 2 to the 4th, which is 4 times 4, which is 16. So I'm going to get x squared is equal to, I'm going to add 1 to both sides, so I get 17. So x is equal to plus and minus the square root of 17. I took square root of both sides. Because I had x already isolated, I was able to solve this way. Now I need to check. If I take the 4th root of negative square root of 17, the quantity squared minus 1, does that equal 2? And since I end up with the 4th root of 16, that does indeed equal 2. And the same thing is going to be true when I take the 4th root of the square root of 17 squared minus 1, that does indeed also equal 2. Part C here, I'm going to have the square root of x minus 1 is equal to negative 4. I'm going to write no solution. And that's because a square root is never going to equal a negative number, and I don't have to do any other work. On part D here, I'm going to go ahead and square both sides. So I'm going to square this side. I'm going to square this side. Left-hand side, I get x plus 7. The right-hand side, I'm going to get x squared plus x plus, or 2x plus 1. I need to subtract x from both sides and 7 from both sides. So I'm going to get 0 is equal to x squared plus x minus 6. So I'm going to end up with 0 is equal to x minus 2, x plus 3. So my two solutions are x is equal to 2 and negative 3. Now I'm going to do the check. The square root of 2 plus 7, does that equal 2 plus 1? Well, this is a square root of 9. That does indeed equal 3. So we know that one checks. Now I'm going to check the other one. The square root of negative 3 plus 7, does that equal negative 3 plus 1? Well, on the right-hand side, or on the left-hand side, I'm going to get the square root of 4. On the left-hand side, I'm going to get negative 2. That does not check. So this is extraneous. So my only solution is that. Now, what do we do when my radical, my exponent is a rational number? So instead of just being 1/2, it's now 2/3. What I need to do is I need to follow this rule. If I have a to the m over n, this is a to the 1 over n multiplied by m. Or similarly, I can write this as a to the m times 1 over n raised to the 1 over n, which can be wrote this way or this way. And the way I eliminate this from both sides is I'm going to raise each side to the 3 over 2, because 2 over thirds multiplied by 3 over 2 is going to produce 1. So what I do to one side, I must do to the other. So I get x is equal to, and I'm going to take the square root of 16 first, and then I'll cube it, because it's easier for me without a calculator. So I get x is equal to the square root of 16 is 4 cubed, so x is equal to 64. And then I should actually check that to make sure that works. On this one, I'm going to go ahead and raise this to 4/3 of both sides, so 4/3. I get x minus 1 is equal to 8 raised to the 4/3. So I'm going to take the cube root of 8, because I can do that without any work, without a calculator. That is, cube root of 8 is 2 raised to the 4th power. So I've got x minus 1 is equal to 16. So x is equal to 17. And I should check to make sure that works. Lastly, I'm going to multiply both sides by 3 over 1. So I have x is equal to negative 64. And that's it for this video. I should actually all check these, but I'll let you check them. We'll see you in class.